Imagine it's August 2008. Netflix is not the global streaming giant you know today. It's a scrappy DVD by mail company, fighting for its life against Blockbuster. And on a hot summer Tuesday, their entire world comes crashing down. A single massive database corrupts. Not just a little glitch, a catastrophic failure. For 3 agonizing days, the company is paralyzed. They can't process orders. They can't update customer queues. They can't ship a single red envelope. 3 days of digital silence. Their business, their future, everything they had built flatlined. Inside their headquarters, engineers worked around the clock in a state of controlled panic. They were staring into the abyss. This one single point of failure, this one monolithic piece of technology, had the power to kill their entire company. And when they finally painstakingly brought the system back online, they made a vow. A promise that would not only save Netflix but would fundamentally change the architecture of the entire internet. The vow was simple: never again. Never again would they be at the mercy of a single fragile system. They had to build something different, something resilient, something that could withstand not just glitches but total catastrophic failures of its own components and keep running as if nothing had happened. They had to learn how to build for chaos. What you're about to learn in this video is the secret that was born from that failure. It's the hidden engine that now powers not just Netflix but Amazon, Google, Spotify, and virtually every major tech company on the planet. This isn't just some obscure piece of code. This is the invisible operating system for the cloud, the master conductor of the digital world. And understanding it is rapidly becoming the single most valuable skill in the technology industry today. This is the story of orchestration. And by the end of this, you won't just understand what it is. You'll understand why it is the most powerful force in modern computing. You see, the problem Netflix faced wasn't unique. It's a problem of success. It's the problem of scale. Think about it like building a city. In the early days, you can build one giant skyscraper to house everyone. All your services, your databases, your user logins, your payment processing. It's all in one massive, tightly connected building. It's simple. It's easy to manage when you're small. But what happens when your city's population explodes? That one skyscraper becomes impossibly crowded. A fire on the 10th floor takes out the entire building. A plumbing issue in the basement shuts down everything. Adding a new wing requires shutting down the whole structure for renovations. This is a monolith. And it's exactly what brought Netflix to its knees. The solution seems obvious when you think of it in terms of a city. You don't build one giant skyscraper. You build a sprawling metropolis of thousands of individual buildings. Each building has its own plumbing, its own electricity, its own purpose. One building handles residential. Another handles commerce. Another handles utilities. If one building catches fire and burns to the ground, the rest of the city doesn't even notice. The fire department shows up, clears the rubble, and a new identical building is constructed in its place automatically. The city doesn't just survive, it heals itself. This is the fundamental idea that Netflix and Amazon stumbled upon. They needed to stop building a single fragile skyscraper and start building a self-healing, infinitely expandable digital city. They needed to break their massive application down into hundreds, then thousands of tiny independent services. Each service would do one thing and do it well. A service for the search bar. A service for your recommended for you list. A service for processing your credit card. A service for streaming the actual video file. Each one is a separate building in the city. But this creates a brand new, even bigger problem. An absolutely massive one. If you have a city with 10,000 buildings, how do you manage it all? How do you make sure every building has power and water? How do you route traffic between them? How do you know when a building has collapsed, and how do you automatically rebuild it in seconds? Who plays the role of the city planner, the power company, the traffic control, and the emergency services all at once? You can't do it with a spreadsheet and a team of people. The scale is just too immense. You need an automated, intelligent system to run the city for you. You need a digital mayor. That right there is the secret. That is orchestration. It's the invisible intelligence that manages the chaos. It's the software that tells all the other pieces of software what to do, where to run, and how to talk to each other. It's the ghost in the machine that ensures when you click play on your TV in Ohio, a tiny dedicated piece of software spins into existence on a server in Virginia, finds the exact video file you requested from another server in Oregon, and streams it to your screen flawlessly, all in less than a second. And it does this for 200 million other people at the same time. Now, why should you care? because this isn't just an interesting story about a tech giant. This shift from the single skyscraper to the smart city is the single biggest revolution in software development in the last 20 years. And the people who understand how to design, build, and manage these digital cities are becoming the most sought-after, highest-paid engineers in the world. This knowledge is a career supercharger. It's the difference between building a small house and being the master architect of an entire metropolis. And it wasn't just Netflix. Across the country in Seattle, another giant was facing the exact same problem, but on an even more terrifying scale. Amazon. Long before Netflix had its crisis, Amazon was dealing with the crushing weight of its own success. Their website wasn't one application. It was a tangled web of hundreds of applications built by thousands of developers, all welded together over years. It was slow, brittle, and impossible to update quickly. A small change in the code for the shopping cart could accidentally break the book recommendation engine. So their legendary CEO Jeff Bezos issued a now-famous mandate. Every single team from that day forward had to build their software as small independent services. These services had to communicate with each other through a standardized method and nothing else. They weren't allowed to directly access each other's databases or link to each other's code. It was a painful, expensive, multi-year transition that many thought was insane. But it worked. It transformed Amazon from a slow-moving online bookstore into the agile, unstoppable technology and logistics behemoth it is today. It allowed them to innovate at a blistering pace and, most importantly, it gave birth to the cloud computing industry itself with Amazon Web Services, or AWS. Both of these titans, Netflix and Amazon, started with the same crippling problem of scale. They both arrived at the exact same solution: break the monolith into a city of microservices. And they both realized they needed a powerful brain, an orchestrator, to manage the resulting complexity. For years, they built these secret, complex systems in-house. They were their crown jewels, their competitive advantage. It was magic. But then, something incredible happened. A team at Google, who had been running their own internal version of this for over a decade, decided to release an open-source version of their secret project to the world. And it changed everything. They created a tool that gave every company, from the smallest startup in a garage to the largest enterprise, the same superpower that only Google, Amazon, and Netflix had. They gave the world a master city planner. This is the core of what we're going to unpack. We're going to pull back the curtain on this technology. We're not just going to talk about theory, we're going to understand how it actually works. How does this orchestrator know when a service is sick? How does it route traffic? How does it allow a company like Netflix to update its application thousands of times per day with you, the user, never noticing a thing? To truly grasp this, we have to start with the fundamental building block. We have to forget the sprawling city for a moment and zoom in on a single revolutionary new type of building. A building that's not made of bricks and mortar, but of pure code. A magical, standardized box that can hold any piece of software and run it perfectly anywhere on any computer, from a developer's laptop to a massive server farm in the cloud. This box is the key. It's what made the modern digital city possible. Understanding this box is the first step to understanding the entire kingdom of cloud computing. And this box has a name. In the world of cloud computing, we call it a container. And this simple, elegant concept is the invisible engine behind the modern internet. It's the reason your Netflix stream almost never buffers, your Amazon order is processed in milliseconds, and the app on your phone gets updated with new features seamlessly while you sleep. It's the unsung hero that allows a handful of engineers to build and manage systems that serve hundreds of millions of people. But to truly grasp how revolutionary this container is, we first have to understand the world that existed before it. A world of digital inefficiency, frustration, and colossal waste. Imagine for a moment you're a software developer, let's say 10 or 15 years ago. Your job is to build an application, a small piece of a website, maybe the part that handles user logins. You write the code on your laptop. It works perfectly. You've tested it 100 times. It's flawless. Now, you have to get that code running on the company's powerful servers so that actual customers can use it. And this is where the nightmare begins. Your laptop runs on one operating system, maybe a specific version of Windows. The server runs on a completely different one, a flavor of Linux. The programming language version on your laptop is slightly different from the one on the server. The helper programs, the libraries your code depends on, are all different versions. So you hand your code over to the operations team and it breaks. Horribly. Crashes. It throws errors they've never seen before. You get a frustrated email back. You look at it, and you say the 5 most infamous words in all of software development. But it works on my machine. This single problem cost companies billions of dollars in wasted time, delayed projects, and outright failures. It was a constant war between the developers who built the software and the operations teams who had to run it. The digital world was a Tower of Babel, where everyone was speaking a slightly different language, and nothing ever quite fit together. The first attempt to solve this was a powerful but brutish technology called the virtual machine, or VM. A VM is exactly what it sounds like: an entire computer, simulated in software. Imagine you want to build a house. The old way, the VM way, is to buy a plot of land, pour a complete concrete foundation, build the entire frame, run all the plumbing and electrical, put up drywall, and install a roof, just to house one single application. If you needed to run another separate application, you had to build another entire house right next to the first one with its own foundation, its own plumbing, its own roof. Each VM had to include not just the application code, but a full copy of an entire operating system, Windows, Linux, whatever it needed. This was a massive leap forward, don't get me wrong. It solved the "it works on my machine" problem because you could now give the operations team not just your code, but a perfect digital replica of your entire computer, the whole house. But look at the cost. These virtual machines were huge. They could be tens of gigabytes in size. They were slow to start up, taking minutes to boot an entire operating system just to run a small piece of code. And they were incredibly wasteful. You had 10 applications running on a server, you had 10 full copies of an operating system, all consuming memory, processing power, and disk space. You were building 10 mansions on one city block when all you really needed were 10 apartments. The digital city was filled with these giant, inefficient mansions. It worked, but it was slow, expensive, and clumsy. Innovation crawled at a snail's pace. Getting a new feature from a developer's idea to the customer could take months of painful coordination. This is the world that the container was born into. And it didn't just improve things, completely changed the game. The genius of the container is its analogy to the real world. The humble shipping container. Before shipping containers, loading a cargo ship was a chaotic nightmare. You had barrels of one size, crates of another, sacks of grain, loose lumber. Every ship had to be packed by hand, a custom job every single time. It was slow, inefficient, and things always got broken. Then, in the 1950s, a simple idea emerged. What if we put everything into standard-sized steel boxes? Suddenly, it didn't matter what was inside. A crane could pick up a box of bananas with the exact same equipment it used to pick up a box of car parts. The boxes could be stacked neatly on ships, trains, and trucks. The global economy exploded because the friction of moving things had been virtually eliminated. The software container does the exact same thing for code. A developer takes their application, the login service from our example, and they package it inside a digital container. But here's the magic. They don't just put the code in there. They also package every single thing that code needs to run. The specific version of the programming language, the exact libraries it depends on, the configuration files, everything. It's a complete, self-contained, hermetically sealed unit. The developer creates this perfect little box on their laptop, and that exact same box can be handed off to be run anywhere else, on another developer's computer, on a test server, or on a massive server in an Amazon data center. The "it works on my machine" problem? Gone. Forever. Because you're no longer just shipping the code, you're shipping the entire environment. The container is a guarantee. If it runs here, it will run there. It will run everywhere. Now you might be thinking, wait, that sounds a lot like the virtual machine you just described. And this is the most critical distinction, the detail that makes containers so powerful. Remember, our VM was a whole house? A container is more like a sleek, modern apartment inside a large apartment building. A virtual machine has to virtualize the hardware and run a whole guest operating system. The house needs its own foundation, its own plumbing, its own electrical grid. A container, on the other hand, is much smarter. All the containers running on a server share the same underlying operating system of the host machine. They share the same foundation, the same main plumbing, the same electrical grid of the apartment building. The container only packages up the unique things the application needs, the furniture and decorations for that specific apartment. This means containers are unbelievably lightweight and fast. A VM can be tens of gigabytes. A container can be just a few megabytes. A VM can take minutes to start. A container can start in a fraction of a second. On a single server where you could maybe run 10 or 12 virtual machine houses, you could run hundreds, even thousands of container apartments. This was the earthquake. Suddenly, companies like Google, Netflix and Amazon could pack their servers with incredible density, saving enormous amounts of money on hardware and electricity. Developers could build and test new features at lightning speed, because they could spin up these tiny disposable environments in an instant. The entire process of building and shipping software went from being a slow, artisanal craft to a high-speed, automated assembly line. This is the first secret. The raw material of the modern cloud isn't the code itself. It's the container that holds the code. It's the standardized box that made everything else possible. But this incredible new power created an entirely new, and much bigger problem. It's one thing to manage a dozen virtual machines. It's like being the landlord for a small neighborhood of 12 houses. It's manageable. But what happens when you demolish those houses and build a skyscraper with 5,000 apartment-style containers? What happens when Netflix needs to run not thousands but hundreds of thousands of these containers, all talking to each other, all needing to be started, stopped, updated, and monitored every single second of every single day? You can't do it by hand. No army of humans could possibly keep up. When you click play on a movie, dozens of these little containers might spring into existence just for you. One to check your account, one to find the video file, one to adjust the streaming quality for your internet speed, one to track your viewing history. When you're done, they vanish. How do you manage that? How do you coordinate a sprawling, chaotic city of millions of these constantly changing digital apartments? You need a system. You need a brain. A digital city planner that automatically manages traffic, power, and resources, deciding which containers should run, where they should run, and what to do when they fail. You need a conductor for this massive digital orchestra. And that conductor, that master brain, is the true secret behind how these companies achieve their mind-boggling scale. That is the world of orchestration. So what is orchestration really? Let's stick with that orchestra analogy for a moment because it's almost perfect. Imagine you're trying to build a website as complex as Netflix. Your website isn't one single piece of music. It's a symphony with hundreds, even thousands of different parts. You have the part that handles user logins, that's your violin section. You have the part that recommends what to watch next, that's the cellos. The part that actually streams the video, that's the entire brass section, blaring at full volume. The part that processes your credit card payment, that's the percussion, precise and always on beat. Now, in the old days of the internet, you'd hire each musician individually. You'd give them their sheet music, a chair, and a music stand. You'd say, okay, violins, you sit here. Cellos, you sit over there. Each musician is a server, a physical computer in a data center. If the first violinist gets sick and goes home, what happens? Silence. The violin part is gone. The symphony is ruined. Your website is down. Someone, a poor engineer, will call Dave. Gets a pager alert at 3 a.m. Dave has to drive to the data center, find a replacement violinist, give them the sheet music, and get them playing again. This is manual. It's slow. It's a nightmare. This is how we used to build things. We treated our servers like pets. We gave them names like Zeus or Apollo. We carefully nurtured them, upgraded them by hand, and when they got sick, we did everything we could to nurse them back to health. If the Zeus server went down, it was an all-hands-on-deck emergency. Companies like Amazon and Netflix realized this model was a complete dead end. You cannot build a global-scale service on a foundation of pets that require constant manual care. You can't have a million pets. So they pioneered a new philosophy, a brutal but brilliantly effective philosophy. They stopped treating servers like pets and started treating them like cattle. Think about it. On a massive cattle ranch, you don't give each cow a name. You don't nurse a sick cow back to health for weeks. The herd is what matters. The individual is disposable. If one animal has a problem, it's quickly and automatically replaced to ensure the health of the overall herd. This is the absolute core, the fundamental mindshift that powers the modern cloud. In this new world, servers are anonymous, identical, and disposable. They don't have cool names like Zeus. They have serial numbers like worker node 87Z, and if that node fails, if it gets sick, you don't fix it. You terminate it. Instantly. And a new, perfectly healthy, identical one is created to take its place in milliseconds. The herd, your application, never even notices. That is what orchestration does. It's the rancher. It's the conductor. It's the master brain that manages the herd. You don't tell it how to do its job. You just tell it what you want the final outcome to look like. This is a concept called desired state. You write a configuration file, which is like the conductor's musical score. In that score you write, I want a symphony that consists of 100 violins, 50 cellos, and 30 brass instruments. They must always be playing in tune. That is the desired state. The orchestrator reads that score. It looks at the orchestra pit, your cloud servers, and sees you only have 98 violins. It doesn't panic. It doesn't page Dave at 3 a.m. It simply says, I need 100 violins, but I only see 98. I will create 2 more. And poof, 2 new violinists, fully trained with their sheet music, appear in their chairs and start playing. Then maybe one of the cello players hits a wrong note, a server starts running slow or has an error. The conductor notices this deviation from the score. It doesn't go over and try to tune the cello. It simply points and that faulty cellist vanishes, and a brand new one instantly takes its place. The conductor's only job is to relentlessly, obsessively, and automatically ensure that reality matches the desired state written in the score. That's it. Self-healing, self-scaling, automatic. When you press play on Netflix, you are witnessing the greatest symphony ever performed. You're not just making one request to one server. Your single click unleashes a cascade of events, a flurry of messages between thousands of tiny specialized services, the microservices we talked about. The login service validates your account. The recommendation service queries its massive database to decide what you'd like to see. The licensing service checks if Netflix even has the right to show you that movie in your country. The content delivery service finds the copy of the movie on a server that's physically closest to your house to give you the best quality stream. Dozens, maybe hundreds, of these tiny cattle-like services all have to coordinate flawlessly in the blink of an eye. The orchestrator is what makes that possible. It ensures that there are always just enough of each of these microservices running to handle the load. When everyone in America sits down to watch the latest hit show on a Friday night, the orchestrator sees the massive spike in demand and says, I need more cattle. A lot more. It automatically scales up the herd, provisioning thousands of new servers in seconds. Then, when everyone goes to bed, it scales the herd back down so Netflix isn't paying for servers they aren't using. But here's where it gets truly mind-bending. This is how you can tell Netflix truly mastered this philosophy. They weren't just content with a system that could survive failure. They wanted a system that was so tough it treated failure as a normal everyday event. So they built a monster. A piece of software they unleashed inside their own systems. They called it Chaos Monkey. The entire job of Chaos Monkey is to run around inside Netflix's live, production environment, the one you are actively using, and break things. On purpose, it randomly terminates servers. It severs network connections between services. It creates mayhem and destruction, intentionally, all day long. This sounds like absolute insanity. Why would you pay engineers to build a tool specifically designed to destroy your own website? Because it was the ultimate test for their orchestrator. It was the ultimate vote of confidence in the cattle not pets philosophy. The system had to be so resilient, so self-healing, that it wouldn't even flinch when Chaos Monkey went on a rampage. If a server vanished, the orchestrator had to be fast enough to replace it before any customer noticed. If the recommendation service suddenly couldn't talk to the login service, it had to be smart enough to reroute the traffic through a different path. They institutionalized failure. They made it a daily workout. By constantly punching their own systems in the face, they built a level of resilience that their competitors could only dream of. They built an anti-fragile system. A system that literally grows stronger from stress and chaos, not weaker. This entire philosophy was born out of necessity. Amazon in the early 2000s was facing the same scaling problems with its retail website. Their internal teams were building these incredible tools to manage their own massive, sprawling infrastructure, tools for automatically provisioning servers, managing databases, and orchestrating complex workflows. Then they had a light bulb moment. They realized that the powerful automated infrastructure they had built to run Amazon.com was a product in itself. Perhaps an even bigger product than the retail store. And that was the birth of Amazon Web Services, or AWS. They took their internal orchestration and automation tools, cleaned them up, and started renting them out to the world. They were the first to truly sell the cattle not pets philosophy as a service. They gave startups the power to build systems with the same resilience as Amazon, without needing a billion-dollar data center. So this isn't just a technical detail. It's a complete paradigm shift in how we think about building software. It's the difference between building a single, beautiful, handcrafted sandcastle and building a beach where the tide can wash away 1,000 grains of sand every second, and the beach remains unchanged. The question is, how do you actually do this? What does that conductor score look like? What is the language of orchestration? For years, there were many different conductors, all competing to be the standard. But in the last decade, one has emerged as the undisputed king, the Beethoven of the cloud, an open-source project started by Google, built on the lessons they learned running services like Search and Gmail at a scale that is almost impossible to comprehend. That tool is the de facto language of modern cloud orchestration. That tool is Kubernetes. Kubernetes. It's a Greek word, meaning helmsman or pilot, the one who steers the ship. And that is the most perfect description of what it does. It doesn't row the oars, it doesn't hoist the sails. It stands at the helm and steers the entire fleet of modern technology through the chaotic, unpredictable waters of the internet. But to truly understand the power of Kubernetes, we need a better analogy than a ship. Because we're not talking about one vessel, we're talking about millions of moving parts. So I want you to forget about code for a minute. Forget about servers. I want you to think about a city. Imagine you are a master city planner, given a blank plot of land and a set of architectural blueprints. Your job is to build and run a thriving, dynamic metropolis that never ever sleeps. This isn't just any city. It's a digital city, and its citizens are the billions of clicks, searches, and video streams happening every second. In this analogy, the physical servers, the computers in those massive data centers we talked about, are the plots of land. A collection of these plots forms your city grid. We call this a cluster. Now, what do you build on this land? You build structures. In the world of Kubernetes, the most fundamental structure is something called a pod. Think of a pod as a building. It could be a small residential home, designed to do one specific job, like serving a single web page. Or it could be a multi-story office complex, a database that holds all your customer information, or a massive factory that processes huge amounts of data. These pods are the fundamental building blocks of our digital city. But here's where it gets interesting. As the master planner, you don't go out with a hammer and nails. You don't lay a single brick. Instead, you operate from a central planning office, what Kubernetes calls the control plane. And you work with blueprints. These blueprints are simple text files, written in a format called YAML, that describe exactly what you want your city to look like. You write a blueprint that says, I need a residential district with 50 identical houses. You hand this blueprint to the control plane. You don't say which plots of land to build on. You don't say how to construct them. You simply declare the desired state. 50 houses right here, right now. And the magic begins. The control plane, your automated construction firm, reads the blueprint and springs into action. It finds 50 empty plots of land across your entire city grid and instantly constructs the houses, the pods, exactly to your specifications. This is the first secret of Kubernetes. It's declarative. You declare what you want the world to look like, and the system makes it so. This is a monumental shift from the old way, which was imperative. The old way was like giving a construction crew a list of turn-by-turn directions. Go to plot A7, dig a foundation, pour the concrete, wait 24 hours, frame the walls. If the cement truck got a flat tire, or the lumber was delayed, the whole process would grind to a halt, and you'd have to intervene manually. The declarative model is different. You just hold up the blueprint and shout, make the city look like this. And the system handles every single detail, obstacle, and error along the way. Now, what happens when one of those houses suddenly collapses? Maybe there's a digital earthquake, a server crashes, a network cable gets unplugged. Does the city grind to a halt? No. This is the second and perhaps most powerful secret of Kubernetes. The control plane isn't just a construction firm. It's a relentless, sleepless city manager. It is constantly watching. 24 hours a day, 7 days a week. It runs what's called a reconciliation loop. It continuously compares the blueprint of the ideal city, the one you declared, with the actual real-time state of the city. The moment it sees a discrepancy, the moment it counts 49 houses instead of the 50 on the blueprint, it doesn't send you an alert. It doesn't wait for instructions. It instantly identifies the collapsed house, marks that plot of land as unstable, finds a new, healthy plot somewhere else in the city, and builds an identical replacement house. All of this happens in seconds automatically without a single human touching a keyboard. This is self-healing. This is the resilience that powers Netflix. When you're binge-watching a show, you are interacting with dozens, maybe hundreds of these little buildings, these pods. One handles your login. Another fetches your continue watching list. Another finds the video file. Another streams it to your device. If any one of those pods fails midstream, Kubernetes instantly replaces it. The new pod picks up right where the old one left off, and your video doesn't even stutter. You are completely oblivious to the controlled chaos being managed behind the scenes. But a city is more than just buildings. How do people find their way around? How does the pod handling your login know how to talk to the pod that holds your account information? The buildings might be torn down and rebuilt in different locations at any time. An address system based on a specific plot of land would be useless. So Kubernetes provides the city services. It builds a network of roads, street signs, and a postal service. In technical terms, this is called a service. You can create a permanent, stable address like the post office that always points to the correct, functioning building, no matter how many times that building is demolished and rebuilt on a different plot. So one part of an application can reliably find another, creating a seamless, interconnected web of services. And what about a sudden rush hour? Imagine a new season of a blockbuster show drops on Netflix. Suddenly, millions of people want to access the streaming service buildings all at once. The digital roads become congested. Well, the city planner sees this coming. Your blueprint can include a rule that says, if the traffic to this type of building exceeds 80% capacity, automatically build more of them. So, as the demand spikes, Kubernetes starts building copies. 10 buildings become 100, become 1,000, all automatically to handle the load. And when the rush hour ends and traffic dies down, it automatically demolishes the extra buildings to save resources. This is autoscaling, and it's how companies like Amazon and Netflix can provide a smooth experience to millions of simultaneous users without crumbling under the pressure. This entire concept, this digital city planner, is the engine of the modern cloud. It's an abstraction layer. It allows developers at these giant companies to stop thinking about individual servers. They no longer care if their code is running on server number 8675 in a rack in Virginia or server number 2309 in a rack in Oregon. They just hand their blueprint to Kubernetes and trust that the city will be built, maintained, and healed, regardless of the chaos happening on the ground. It's a system born from Google's 15 years of experience, running the world's largest containerized workloads. They learned the hard lessons of managing billions of containers for services like Search and Gmail, and they distilled that knowledge into this open source tool, giving it to the world. So now we have this beautiful, abstract picture of a self-healing, auto-scaling digital city. We understand the philosophy. Declare your perfect world, and let the machine work tirelessly to create it. But this is still the 30,000-foot view. We've talked about the blueprints and the city planner, but what are the actual bricks and mortar made of? What exactly is inside one of those pods? And what are the different kinds of blueprints we can give our city planner to build even more complex and powerful structures? To understand that, we have to zoom in. We have to leave the planner's office, walk down to the street level, and look at the nuts and bolts of how this digital metropolis is actually put together. At the street level of our digital city, before the master planners arrived, things were chaotic. It was the age of the artisan builder. Imagine every single application, every piece of software was like a custom-built house. A developer, the artisan, would construct it right there on the plot of land, the server. They'd lay the foundation, which was the operating system. Then, they'd painstakingly assemble the framework, the libraries, the dependencies, all the specific tools the application needed to run. They'd install version 2.7 of this and patch 1.3 of that, and configure a specific database connection over here. When they were done, they had a beautiful, functional house. It worked perfectly on that specific plot of land. But then the business would say, "This is great. We need another one just like it for our new server farm in Ohio." So the artisan would travel to Ohio to a new, empty plot of land and try to build the exact same house. But maybe the soil was different. The underlying server hardware wasn't quite the same. Maybe the local building code had changed. The operating system was a slightly different version. They tried to assemble the same framework, but now the supplier only had version 2.8 of that one tool, and it wasn't quite compatible with the old plumbing fixtures. This was the "it works on my machine" nightmare, a problem that plagued software development for decades. Every server was a unique, fragile ecosystem. Moving an application from a developer's laptop to a testing server, and then to the live production server, was a journey filled with anxiety, late nights, and unpredictable failures. Scaling up was a nightmare. You couldn't just copy and paste the house. You had to rebuild it from scratch every single time, hoping you remembered every single nail and screw. This artisan approach was slow, it was expensive, and it was incredibly fragile. The digital world couldn't build a metropolis this way. It needed a revolution. And that revolution, funnily enough, was inspired by a real-world invention from the 1950s that has almost nothing to do with computers: the shipping container. Before 1956, global trade was chaos. If you wanted to ship goods, you'd send them to the docks in whatever form they came in: sacks of coffee, barrels of oil, crates of electronics, loose bundles of textiles. Longshoremen would spend days, sometimes weeks, manually loading these mismatched items into the hold of a ship, fitting them together like a bizarre, three-dimensional jigsaw puzzle. It was incredibly inefficient, prone to theft and damage, and astronomically expensive. Then, a trucker from North Carolina named Malcolm McLean had a ridiculously simple idea. What if, instead of loading all this mismatched cargo, we first loaded it into big, identical, standardized metal boxes? And then we could just lift the boxes onto the ship. And then lift the same boxes off the ship and onto a train or a truck without ever opening them. Sounds obvious now, but it was revolutionary. The intermodal shipping container standardized the very atom of global trade. A crane didn't need to know if it was lifting luxury cars or cheap t-shirts. It only needed to know how to lift the box. This one simple idea slashed shipping costs by over 90%, dramatically reduced transit times, and unlocked the modern era of global commerce. One standard box changed the world. A software container is the digital equivalent of that revolution. The brilliant minds in tech looked at the "it works on my machine" problem and realized they were dealing with the same chaos as those old shipping docks. Every application was a custom-sized barrel or a weirdly shaped crate. The solution was to create a standard box for code. This box is called a container, and the most famous brand of these boxes is called Docker. A container takes the application, the code that makes Netflix stream a movie or Amazon process your order, and it packages it up with everything it needs to run. All the right versions of the libraries, all the specific tools, all the configuration files. It's all sealed inside one neat, tidy, standardized digital box. Now the developer doesn't hand over a complicated set of blueprints and a box of parts. They just hand over the finished container. And that container will run identically, perfectly, first time, every time, whether it's on a developer's laptop in a coffee shop in Seattle, a test server in a lab in Austin, or a massive cloud server in Virginia. The underlying plot of land no longer matters. The box is self-sufficient. The "it works on my machine" problem? Solved. Forever. But here's where it gets really clever, and where it diverges from our house analogy. You might be thinking, wait, haven't we had this for years? It's called a virtual machine or a VM. And you'd be right, kind of. A virtual machine was the old way of solving this. A VM is like building a complete, self-contained house, foundation and all, on a larger property. It includes not just the application and its dependencies, but an entire guest operating system inside it. It has its own virtual Windows or its own virtual Linux, completely separate from the main server's operating system. This works, but it's incredibly heavy. Each VM is carrying the massive overhead of a full operating system. It's like building a suburb of single-family homes. Each house has its own foundation, its own roof, its own duplicate infrastructure. It takes up a lot of space and it takes a long time to build. A VM can take several minutes to boot up. Containers are different. Containers are more like apartments in a high-rise building. Dozens, even hundreds of containers can run on a single server. They all share the same foundation, the host server's operating system kernel. But each apartment is completely sealed off and isolated from the others. The application running in Container A has no idea that the application in Container B even exists. They have their own private space, their own plumbing and wiring, their dependencies, but they share the building's core infrastructure. They share the foundation, but they don't share a bathroom. This makes containers impossibly lightweight and mind-bogglingly fast. A container doesn't need to boot up an entire operating system. It just needs to start its one specific process. We're not talking about minutes. We're talking about seconds or even milliseconds. The impact of this is staggering. First, speed. For a company like Netflix, when 1 million people suddenly decide to watch the new hit show on a Friday night, they can't wait minutes for new servers to boot up. They need to spin up hundreds or thousands of new copies of their streaming application in seconds. Containers make that possible. Second, efficiency. Because containers are so lightweight, you can pack them onto servers with incredible density. Instead of a server running maybe 10 heavy virtual machines, that same server might be able to run 100 or even 1,000 lightweight containers. This translates into a colossal reduction in cost. You need fewer servers to do the same amount of work, which means less hardware, less power, less cooling. For a company operating at the scale of Amazon, This shift saves hundreds of millions of dollars. And third, consistency. The container becomes the universal contract between the developers who build the software and the operations teams who run it. The developers build and test the box. The operations team just has to deploy the box. There are no more misunderstandings or configuration errors in the handoff. It's a perfect sealed unit of software. So this is the secret at the street level. This is the nut and the bolt. The standardized, prefabricated apartment unit of the cloud. The container. It brought order to the chaos. It allowed for speed, efficiency, and reliability on a scale that was previously unimaginable. We now have the perfect building block. A lightweight, portable, self-contained box that can be created in an instant and deployed anywhere. But this incredible solution creates a brand new problem. Problem of scale. It's one thing to manage a dozen containers. You can keep track of them manually. But what happens when you're Netflix and you need to run hundreds of thousands of these containers? What happens when you're Amazon, and you might have millions of them running across the globe, all talking to each other, constantly starting, stopping, and updating? You can't manage that by hand. You'd need an army of people just to keep track of what's running where. We've solved the problem of the brick. But in doing so, we've created the problem of the city. How do you decide which server a new container should run on? How do you connect container A to container B so they can talk to each other? What happens if a server goes down, taking 100 containers with it? How do you automatically replace them? How do you roll out an update to 10,000 containers without taking your entire service offline? You need a system. You need a brain. You need to zoom back out from the street level and return to the planner's office. You need a master architect for your city of containers. You need an orchestrator. And in this new world, 3 titans emerged to compete for the role of master architect. 3 different philosophies on how to build and manage these sprawling digital cities. This wasn't just a technical debate. It was a war for the soul of the cloud, a battle to become the brain of modern infrastructure. In one corner, you had the grassroots revolutionary Docker swarm. In another, the established empire, Amazon, with its own creation, ECS. And then there was the one that came from the gods of scale themselves, the one born inside the machine that organizes the world's information, the one called Kubernetes. To understand Kubernetes, you have to go back to Google. For over a decade, long before anyone was talking about containers publicly, Google was living in the future. They weren't running thousands of containers or even millions. They were running billions of containers. Every week. Every Google search, every Gmail you send, every YouTube video you watch. All running in containers. But to manage that impossible scale, they needed a secret weapon. An internal system they built called Borg. Borg was the culmination of a decade of real-world, planet-scale engineering. It was the battle-hardened master controller that allocated resources, scheduled tasks, and healed itself across Google's massive, global data centers. It was, for all intents and purposes, a legend. A piece of mythical software whispered about in engineering circles. Then, in 2014, Google decided to give a gift to the world. They took all the lessons learned from building and running Borg, distilled them into a new open-source project, and set it free. They called it Kubernetes. The name comes from Greek, meaning helmsman or pilot, the one who steers the ship. And that's exactly what it does. If a container is a single shipping container, and a Docker host is the cargo ship, Kubernetes is the entire port authority, the logistics network, and the captain all rolled into one. Fundamentally changed the game. Instead of you telling the system how to run your application, you simply tell Kubernetes what you want. This is the core revolutionary idea, desired state configuration. Think of it like a thermostat in your house. You don't stand there and tell the furnace, "Okay, turn on for 3 minutes and 27 seconds, then turn off. Then monitor the temperature. And if it drops, turn on again." No, you just walk up to the thermostat and set it to 72 degrees. That's the desired state. You have declared your intent. From that moment on, the thermostat's only job is to constantly compare the current state, the actual temperature in the room, to your desired state. If it's too cold, it turns on the heat. If it's too hot, it turns on the AC. It works tirelessly 24/7 to make reality match your declaration. Kubernetes is the thermostat for your entire application infrastructure, but on a godlike scale. You write a configuration file, a blueprint essentially, that says, "I want 3 copies of my web server running at all times. I want them to have this much memory, this much CPU, and they need to be able to talk to this database. Oh, and I want them to be accessible to the public on port 80. You hand this blueprint to Kubernetes. And it makes it so. It finds a server with enough resources and places your first web server container there. It finds another and places the second, and a third. It then configures the networking so the world can talk to them. It is now in its desired state. But here's the magic. An hour later, a massive surge of traffic hits your website. One of your servers gets overwhelmed and crashes. The container just dies. What do? Nothing. You do absolutely nothing. Because Kubernetes, the relentless thermostat, immediately detects a mismatch. The current state, 2 running web servers, does not match the desired state of 3. So without any human intervention, it instantly spins up a new, perfectly healthy replacement container on another server and seamlessly adds it back into the network. The user who is about to hit your now dead server is automatically rerouted to a healthy one. They never even notice. Your application just healed itself. This is the power. It's a system that doesn't just deploy. It manages, it heals, and it scales, all based on a simple declaration of intent. To do this, Kubernetes has a whole vocabulary. It thinks of your city of containers in a very specific way. At the lowest level, it doesn't just run a container. It runs a pod. A pod is the smallest deployable unit in Kubernetes, and you can think of it as a tiny, single-purpose apartment that holds one or more tightly coupled containers. They share the same network, the same storage, and they live and die together. Usually, it's just one main container, but sometimes you have a helper container alongside it, like a little sidecar that handles logging or data processing. These pods, these tiny apartments, are placed on nodes. A node is just a worker machine. It could be a physical server in your basement or a virtual machine in the cloud. It's the plot of land where you build your structures. And a collection of all these nodes, all working together, forms a cluster. The cluster is your entire digital city. And overlooking this entire city from a skyscraper in the center is the brain of the operation, the control plane. This is City Hall. It's where the API server acts as the front desk, taking your requests. It's where the scheduler, like a master zoning board, decides which node is the best place to build a new pod. And it's where the controller manager acts like the city's public works department, constantly watching to make sure everything is running according to your blueprints. While Kubernetes was being forged in the fires of Google, the creators of the containers themselves, Docker, had their own idea. They created Docker Swarm. If Kubernetes was a sprawling, infinitely customizable metropolis like New York City, Swarm was a clean, elegant, and brilliantly designed city like Portland. It was built on a philosophy of simplicity. It used the exact same Docker commands that developers already knew and loved. Getting a Swarm cluster up and running was breathtakingly simple. It was less powerful, less flexible, and had fewer features than Kubernetes, but for 80% of the use cases it was more than enough. It was the pragmatic choice. Then there was the third titan, Amazon's ECS, or Elastic Container Service. ECS wasn't a piece of software you could download and run anywhere. It was a fully managed service, woven directly into the fabric of Amazon Web Services. If Kubernetes was a city you had to build and govern yourself, and Swarm was a pre-planned town, ECS was like living in an all-inclusive 5-star resort managed by Amazon. You don't worry about the control plane, the servers, or the networking. You just define your application, and Amazon's army of engineers handles the rest. Its superpower wasn't flexibility. It was seamless integration. It connected to Amazon's load balancers, its security systems, its monitoring tools with almost zero effort. For companies already living deep inside the Amazon ecosystem, it was the easy button. So the stage was set. The simple and intuitive Swarm, the powerful and integrated ECS, and the complex open-source behemoth Kubernetes. The entire tech world held its breath. A standard had to be crowned, and then the world chose. Decisively, Kubernetes won. And it wasn't even close. It won for the same reason the internet itself won. It was open, it was neutral, and it belonged to no one. You could run Kubernetes on Google Cloud. You could run it on Microsoft Azure. You could run it on Amazon Web Services. In fact, AWS eventually had to build its own managed Kubernetes service, EKS, just to keep up with customer demand. You could even run it on your own hardware. This freedom from vendor lock-in was the killer feature. An entire ecosystem exploded around it. A massive, passionate community, the Cloud Native Computing Foundation, formed to steward its development. Thousands of developers and hundreds of companies started building tools for Kubernetes. It became a platform for building platforms. A self-reinforcing cycle of adoption and innovation began, and it was unstoppable. Docker eventually designed its desktop software to run Kubernetes. Even Docker Swarm's own creators began to integrate Kubernetes. The war was over. The helmsman was now steering the entire industry. Kubernetes had become the de facto operating system for the cloud. It gave companies of all sizes the same superpower that Google had been using for years: a resilient, self-healing, and infinitely scalable infrastructure. But with this incredible power came an incredible crushing complexity. Handing a developer Kubernetes was like handing them the keys to New York City and saying, "Congratulations, you're the mayor. Don't screw it up. You have the power to do anything, but you're also responsible for everything. The plumbing, the electrical grid, the traffic, the zoning laws." It was overwhelming. A new problem had emerged. We had the perfect brain for the cloud, but who was smart enough to actually operate it? The answer, it turned out, was hiding in plain sight. It was inside the one company that had been living in the future for nearly a decade, Google. While the rest of the world was just starting to grapple with the idea of a few dozen virtual machines, Google was already operating at a scale that was, and frankly still is, almost impossible to comprehend. Think about it. Every single Google search, every email sent through Gmail, every YouTube video watched. All of it was running on a global network of massive data centers. This wasn't just a city. It was a planetary civilization of software. And they had been managing this civilization since the early 2000s with a secret internal system, a piece of software so powerful and so critical to their success that almost no one outside the company had ever heard of it. They called it Borg. Borg was Google's in-house city manager. It was the master puppeteer, the grand conductor, the central nervous system for their entire global infrastructure. Borg was responsible for taking all of Google's applications, from the search index to Google Docs, and scheduling them across tens of thousands of machines spread across the globe. It handled failures automatically. If a server in a data center in Oregon caught fire, Borg would seamlessly move the applications that were running on it to healthy machines in Iowa, without a human ever lifting a finger. It managed resource allocation with ruthless efficiency, packing applications onto servers like a master Tetris player to ensure not a single CPU cycle or byte of memory was wasted. For over 10 years, Borg was Google's secret weapon. It allowed their developers to move at lightning speed. They didn't have to worry about which machine their code would run on, or what would happen if that machine died. They just handed their containerized application to Borg and said, "Here, run this for me, and make sure it never goes down." Borg took care of the rest. It was the ultimate abstraction, the perfect operator for their city of microservices. But by 2013, the world was changing. Amazon Web Services was dominant. The cloud was becoming the new standard, but it was a fragmented world. Every cloud provider had its own way of doing things. If you built your application for Amazon, you were locked into Amazon's tools. The dream of a universal, portable application that could run anywhere was just that, a dream. A few engineers at Google, many of whom had worked on Borg, saw an opportunity. They saw the rest of the world struggling with the very same problems they had solved a decade earlier. They saw the rise of Docker and containers as the perfect building block, the standardized shipping container they had always used internally. And they had a radical idea. What if they took the lessons learned from building and running Borg for over a decade and created a new system from scratch? A system designed not just for Google's private infrastructure, but for the entire world. A system that wasn't a secret but a gift. What if they gave every company on Earth the keys to manage their own digital city, just like Google did? And so, in mid-2014, Google open-sourced a project called Kubernetes. The name comes from the ancient Greek word for a helmsman or a pilot, the person who steers a ship. And that's exactly what it was designed to do: steer the chaotic sea of containers. Kubernetes was the world's first open-source container orchestrator. It was the smart, tireless, and infinitely scalable city manager that the cloud so desperately needed. But how does it actually work? What is the magic that makes Kubernetes the undisputed king of the cloud? It comes down to one profoundly simple, yet revolutionary idea: desired state. Before Kubernetes, you managed your systems imperatively. You gave the computer a series of commands like a recipe. First, start up a server. Second, install this software. Third, configure this network rule. Fourth, start 3 copies of my application. You were responsible for the how. If one of those application copies crashed, it was your job to notice and start a new one. This is exactly the problem that led to the overwhelming complexity we talked about. Kubernetes flips this entire model on its head. With Kubernetes, you manage things declaratively. You don't give it a recipe, you give it a blueprint. You describe the final state you want to achieve. You write a configuration file that says, "This is my desired state. I want 5 copies of my web server running at all times, using this specific container image. They need to be able to talk to my database, and they need to be accessible to the outside world through this address." You hand this blueprint to Kubernetes and you're done. From that moment on, Kubernetes' job, its only job, is to make reality match your blueprint. It has a component called the control plane, the city hall, which is constantly watching the current state of the system. It asks, how many web servers are running right now? If the answer is 4, but the blueprint says there should be 5, Kubernetes doesn't wait for you. It immediately springs into action, finds a healthy machine with available capacity, and starts a new web server container. It's a relentless, self-healing system. If a server completely fails, Kubernetes sees that the containers on it have disappeared. It consults the blueprint, sees they are still required, and instantly recreates them on other healthy servers. You don't have to wake up at 3 a.m. to a pager alert. Kubernetes handles it. It's the tireless operator that never sleeps. This simple concept of desired state is the secret that powers everything. It allows for automated scaling. If your Netflix and a new hit show drops, you can simply change one number in your blueprint from, say, 1,000 servers to 10,000. Kubernetes handles the monumental task of rolling out those 9,000 new copies. It allows for seamless updates. You can give Kubernetes a new version of your application container, and it will perform a rolling update, gradually replacing old containers with new ones one by one, ensuring there is zero downtime for your users. Kubernetes became the operating system for the cloud. The individual servers, whether they were from Amazon, Google, or Microsoft, no longer mattered as much. They were just a generic pool of resources, CPU, memory, and storage for Kubernetes to manage. This was a seismic shift in the industry. It broke the vendor lock-in. An application designed to run on Kubernetes could run on any cloud. And this is where our story comes full circle back to Amazon and Netflix. Netflix, despite being one of Amazon's biggest and most famous customers, saw the power of this Google-born technology immediately. They had thousands of microservices, and managing them, even with AWS powerful tools, was a massive challenge. Kubernetes offered them a universal standard, a common language to describe and manage their complex application architecture. It gave them portability and a way to avoid being completely locked into the Amazon ecosystem. So they became one of the earliest and most prominent adopters of Kubernetes, running it on top of Amazon's servers. Think about the beautiful irony of that. The system that powers Netflix, running on Amazon's cloud, was a spiritual successor to the system that powers Google. This created a tidal wave. Soon everyone wanted to use Kubernetes. Startups, banks, retailers, the entire industry began to standardize on it. The momentum was unstoppable, and this put Amazon in a very difficult position. They had their own proprietary container orchestration service. But their customers, even their biggest ones, were choosing to install and run a competitor's open-source technology on their platform. For years, Amazon resisted, but the market had spoken. In 2017, they finally capitulated. They announced the Amazon Elastic Kubernetes Service, or EKS. They had to offer Kubernetes as a first-class managed service. They had to support their competitors' technology because it had become the undisputed industry standard. The secret was out. The gift that Google gave the world had been so powerful, so paradigm-shifting, that it had forced the hand of the king of the cloud. The problem of the brain without an operator had been solved. We now had the perfect brain, containers, and the perfect central nervous system to manage it, Kubernetes. The city of the cloud finally had its omniscient, all-powerful planner. The orchestra finally had its conductor. But this new, perfectly orchestrated world created an entirely new set of challenges. The city was planned, the buildings were in place, and the traffic was flowing smoothly. But what about the communication inside the buildings? What about the millions of conversations happening between all of these microservices? A new layer of complexity had just been unlocked. This new layer of complexity wasn't just a small wrinkle. It was a fundamental challenge to the entire microservice philosophy. The promise was independence and agility, but what they got was a sprawling, chaotic digital city with no street signs, no secure phone lines, and no way to know if a message ever reached its destination. Imagine trying to run a company where every employee is in a separate soundproof room. To talk to someone, you have to first find their room number, which changes every few minutes. Then you have to shout your message down the hallway, hoping they hear you and that no one else is eavesdropping. If they don't answer, do you shout again? How many times? What if they're just busy versus their room being empty? Now, multiply this problem by 10,000 employees, all trying to talk to each other simultaneously millions of times per second. It's pure, unadulterated chaos. This was the reality for early microservice adopters. The application code, the part that was supposed to be focused on business logic like processing a payment or recommending a movie, was suddenly bloated with networking code. Every single service had to have its own, handwritten logic for service discovery, handling timeouts, retrying failed requests, encrypting traffic, and collecting metrics. It was a nightmare. Developers were spending more time writing boilerplate networking code than they were building features. And worse, every team implemented it slightly differently. A bug in the retry logic of one small service could create a retry storm that brought down the entire platform. The very architecture designed for resilience was creating new spectacular ways to fail. The engineers at places like Google, Netflix, and Lyft knew this was unsustainable. They needed to pull all of that messy, complex networking logic out of the application itself. They needed to separate the what the service does, its business purpose, from the how it communicates. The application shouldn't have to care if it's talking to another service in the same data center or halfway across the world. It shouldn't have to know how to encrypt its own traffic. It should just be able to say, send this message to the billing service, and trust that it gets there securely and reliably. The solution was an idea so elegant and powerful it would change the face of cloud computing. It's called the sidecar pattern. Think of your microservice, your application container, as a high-profile VIP. The VIP's job is to do one thing: make important decisions. That's the business logic. Now, you wouldn't expect that VIP to also drive their own car, check for threats, and navigate through traffic, right? No, you assign them a chauffeur, a bodyguard, a communications expert, a whole team that handles the logistics of getting from point A to point B safely and efficiently. The sidecar is that team rolled into one. It's a separate, ultra-lightweight, and highly specialized container that is deployed right next to your main application container. They live together, they die together. They share the same network space, meaning from the application's perspective, the sidecar is just sitting at localhost. It's like having your personal bodyguard standing right next to you. Here's where the magic happens. All network traffic, both coming into and going out of your application, is intercepted by this sidecar proxy. The application itself isn't talking to the outside world anymore. It's only ever talking to its loyal sidecar. When your user profile service wants to talk to the recommendations service, it sends a simple, unencrypted request to its sidecar. The sidecar takes it from there. It looks up where the recommendation service actually is, opens a secure, encrypted connection to the other service's sidecar, and forwards the request. It handles retries if there's a network blip. It records detailed metrics about how long the call took. The application is completely oblivious to all of this complexity. It just did its job, and the sidecar handled the rest. This is a game changer for a single service. But what happens when every single service in your entire system gets its own sidecar? What you get is a service mesh. The collection of all these sidecar proxies forms what's called the data plane. This is the workforce. They are the ones on the ground sitting next to every application, routing the traffic, encrypting the data, and handling the failures. But who tells them what to do? Who gives them the rules? That's the control plane. The control plane is the brain of the operation. It's a central set of services that configures all of the sidecars. It pushes out policies like, all traffic between the payment service and the fraud detection service must be encrypted using this specific protocol. Or, if the inventory service doesn't respond within 50 milliseconds, consider it a failure and try a different one. Suddenly, that chaotic digital city has an intelligent, invisible infrastructure layer. It's like installing a hyper-efficient, secure telecommunications and transport system overnight. The individual applications don't need to change. They just wake up one morning and find that all their communication problems have been solved for them. With a service mesh in place, engineers gain superpowers. First, security becomes automatic. The control plane can enforce a zero-trust network policy, meaning that by default, no service is allowed to talk to any other service. You then explicitly whitelist the connections you need. And you can mandate that all whitelist traffic is automatically encrypted using mutual TLS, or MTLS. This is huge. It means both sides of the conversation cryptographically verify the other's identity before speaking, creating a secure, end-to-end encrypted tunnel for every single request inside your network. And your developers didn't have to write a single line of code to get it. Second, you get unbelievable control over traffic flow. Want to test a new version of your checkout service? With a service mesh, you can perform a canary release. You tell the control plane, send 1% of live production traffic to the new version. The sidecars will start routing a tiny fraction of requests to your new code. You can monitor its performance and error rates in real time. If everything looks good, you can tell the control plane, okay, ramp it up to 10%. Now 50%. Now 100%. You can perform a major production deployment with zero downtime and minimal risk. You can do A/B testing, traffic shadowing, and fault injection to see how your system behaves when a service fails. And the mesh provides resilience out of the box. The sidecars can automatically retry failed requests. If a service becomes overloaded or unresponsive, its sidecar can trip a circuit breaker, temporarily stopping traffic from flowing to it and preventing a single failing service from causing a cascade failure that takes down your entire application. Finally, and perhaps most importantly, you get observability. Deep system-wide observability. Because every single request flows through a sidecar, the mesh sees everything. It can generate the 3 pillars of observability: metrics, logs, and traces for your entire distributed system automatically. You can get a real-time map of your services, seeing who is talking to whom. You can trace a single user's request as it bounces from the web server, to the authentication service, to the user profile service, to the recommendations engine, and see exactly how long each step took. When something goes wrong, you don't have to guess where the problem is. You can see it. This is the secret that powers the orchestration inside Amazon and Netflix. They were pioneers of these concepts long before products like Istio and Linkerd made them widely available. Netflix built its own internal libraries like Hystrix for circuit breaking and Ribbon for load balancing, which were the spiritual predecessors to the service mesh. Amazon now offers AWS App Mesh, a fully managed service mesh, because they know that for any complex application running on their cloud, this isn't a luxury, it's a necessity. Kubernetes had solved the problem of orchestrating the containers, the buildings in our digital city. The service mesh solved the problem of orchestrating the communication between them, the millions of conversations happening inside. It turned network communication from an application-level concern into a platform-level utility. It's the invisible nervous system, the secure transport layer, the all-seeing eye that makes a complex microservices architecture not just manageable, but reliable, resilient, and secure. The system was alive, it was communicating, it was resilient, but it was still being managed by human hands, and human hands make mistakes. The final piece of the puzzle wasn't about adding more technology, but about changing the fundamental relationship between the developers and the system itself. This new relationship was born from a simple, yet revolutionary mandate. A principle so powerful it would fundamentally reshape how software is built and maintained across the globe. It's a phrase you've likely heard, but its origin and true impact are staggering. The phrase is, you build it, you run it. This concept, famously championed by Amazon's CTO Werner Vogels, was a direct assault on the old way of doing things. For decades, the software world was split by a massive wall. On one side, you had the developers. Their job was to write code, create new features, and push the product forward. Once they were done, they would package up their creation and, in a sense, throw it over the wall to the other side, the operations team. The operations team, or ops, were the gatekeepers of production. Their job was stability. They were responsible for deploying the code, managing the servers, and making sure the website didn't crash. Their primary incentive was to prevent change because change was risky. Every new piece of code was a potential new point of failure. You can see the inherent conflict. Developers were rewarded for moving fast and shipping features. Operations was rewarded for keeping things slow and stable. This created a culture of friction, finger-pointing, and blame. When the site went down at 3 a.m., developers would blame the operations team for a bad deployment. The operations team would blame the developers for writing buggy code. It was slow, it was inefficient, and at the scale of Amazon or Netflix, it was a death sentence. You build it, you run it, smash that wall to pieces. It declared that the small, autonomous team of engineers who wrote the code for a specific microservice were now also responsible for its entire lifecycle. They had to test it, deploy it, monitor it, and crucially, they had to carry the pager for it. Suddenly, the consequences of writing bad code were immediate and personal. If a developer pushed a change with a memory leak that caused the service to crash in the middle of the night, their phone would be the one ringing. Not some anonymous operations person in another department, their own. This single philosophical shift had a cascade of profound effects. First, it forced developers to think like operators from day one. They couldn't just write code that worked on their laptop. They had to write code that was resilient, scalable, and monitorable in the real world. They started building better, more robust software because their own sleep depended on it. Second, it created a culture of ownership. These small teams, Amazon's famous two pizza teams, weren't just responsible for a piece of code. They owned a piece of the business. They were accountable for its performance, its availability, and its success. This is the very organizational structure that mirrored the technical architecture of microservices. Each small independent team owned a small independent service. Form followed function. At Netflix, this philosophy took the shape of what they called the paved road. They understood that you couldn't just hand developers this immense responsibility without giving them the tools to succeed. So, their central engineering teams built a set of world-class, pre-integrated, easy-to-use tools for everything: deployment, monitoring, alerting, and failure testing, the very tools like the Simian army that we talked about earlier. Developers were free to go off-road and use their own tools, but the paved road was the fastest, easiest, and best supported path. This brilliant approach balanced developer freedom with centralized stability. It empowered teams to run their own stuff without having to reinvent the wheel for every single service. It gave them the power of a world-class operations team, but packaged into self-service tools they could control themselves. This is where the true purpose of the orchestrator finally clicks into place. Tools like Borg and later Kubernetes weren't just about managing containers. They were the engine of the you build it, you run it philosophy. They were the ultimate empowerment tool. How? By turning infrastructure into code. Before, deploying an application required a human operator to manually log into servers, configure load balancers, and set up databases. It was a complex, error-prone process documented in checklists and runbooks. Human hands, human mistakes. With an orchestrator, the developer defines the entire desired state of their application in a simple text file, a configuration file. This file says, I need 5 copies of my web server running this specific container image. They each need 1 CPU and 2 GB of memory. They need to be connected to this database, and they need a public-facing load balancer. This file is code. It can be version controlled in Git just like the application code. It can be reviewed by peers. It can be tested. And most importantly, it can be handed to the orchestrator. The orchestrator reads this file and becomes a relentless, automated operator. It compares the developer's desired state with the actual state of the cluster, and it works tirelessly to make reality match the file. If a server fails and one of the 5 copies dies, the orchestrator automatically detects this discrepancy and immediately spins up a new one on a healthy machine. The developer doesn't have to do anything. They don't even need to be awake. This is a fundamental paradigm shift from imperative to declarative. The old way was imperative. You gave the system a list of commands. Do this, then do that, then check this. The new way is declarative. You tell the system what you want the end result to look like. This is the state I want to be in. You declare the outcome, and the system figures out how to achieve and maintain it. This is the secret. This is how you achieve resilience and speed at the same time. You remove the manual error-prone steps. You empower developers to control their own destiny through code. The orchestrator becomes the bridge between the developer's intent and the running, self-healing reality in the cloud. It's the robot army that never sleeps, constantly enforcing the rules laid out in those configuration files. The result was an explosion in development velocity. At Amazon, where this philosophy was born out of necessity, teams could now deploy changes to production hundreds, even thousands of times a day. A bug fix or a new feature didn't need to wait for a weekly maintenance window and a complex handoff to the ops team. The developer who wrote the code could push a button, and the automated system, governed by the orchestrator, would safely roll it out in minutes. This new model, combining the dev and ops disciplines, became known as DevOps. It wasn't a job title or a piece of software. It was a cultural movement. It was the fusion of a microservices architecture, a philosophy of ownership, and the enabling technology of cloud orchestration. These 3 pillars, architecture, culture, and tooling, were the legs of the stool. Without all 3, the entire system would collapse. Amazon and Netflix didn't just build a better way to run servers. They built a better way to build a technology company. They created a system that could scale not just its servers but its people. A system that could move faster with more engineers while simultaneously becoming more reliable. It was a paradox that defied decades of conventional wisdom. But with this new power, this godlike ability to declare a state and have a global computer make it so, came a new terrifying class of problems. Because when a system this complex and this automated fails, it doesn't fail in the ways we're used to. It fails in ways no one had ever seen before. Imagine a single overloaded server in one of Amazon's massive data centers. In the old world, an alarm would blare on an engineer's screen. They'd get a call at 3 a.m., log in, diagnose the problem, and manually launch a new server to help with the load. The process is human, slow, and prone to error. But in the new declarative world, something far stranger happens. The orchestrator, the global brain, sees the server struggling. Its current state, high CPU usage, doesn't match the desired state, which might have a rule that says no server should be over 80% CPU for more than 5 minutes. The orchestrator's only job is to make reality match the declaration. So it acts. It launches a new server. But what if the reason the first server was overloaded was because of a software bug that caused it to get stuck in an infinite loop, consuming all its resources? The new server comes online, gets the same buggy software, and it too goes into an infinite loop, maxing out its CPU. Now the orchestrator sees two servers struggling. The gap between the current state and the desired state is even wider. So it does the only thing it knows how to do: it launches more servers. And then more. And more. This is called a cascading failure. The system, in its relentless robotic attempt to heal itself, is actually amplifying the problem, creating a tidal wave of new servers that are all instantly broken, consuming vast amounts of power and resources, threatening to take down the entire application. The system's immune response has become an autoimmune disease, attacking the very thing it was meant to protect. This is the terrifying paradox of modern orchestration. The automation is so powerful that its failures are equally powerful. The engineers at Google, who were building one of the first true orchestration systems, Borg, faced this problem head-on. They knew they couldn't predict every possible failure. They couldn't write code to handle every strange edge case. The complexity was just too high. So they went back to first principles. They asked a different question. What is the simplest possible pattern that can create a stable, self-healing system, even when individual parts are chaotic and unreliable? The answer they landed on is the single most important concept in cloud computing. It is the secret that underpins everything from how Netflix survives random server crashes to how Amazon processes millions of orders a minute. It's not a specific piece of software. It's an idea. An elegant, powerful, and deceptively simple pattern known as a reconciliation loop, or more commonly, a control loop. Think of the thermostat in your house. It performs a very simple, continuous loop of 3 actions. First, it observes the current state. It measures the temperature of the room. Second, it compares that current state to the desired state, the temperature you set on the dial. Third, if there's a difference, it acts to reconcile that difference. If it's too cold, it turns on the furnace. If it's too hot, it turns on the air conditioning. Then the loop starts over. Observe, compare, act relentlessly 24 hours a day. You don't tell the thermostat how to heat the room. You just tell it the state you want, 72 degrees, and it works tirelessly to make the physical world match your declaration. Now imagine that same simple loop, but instead of a thermostat, it's a piece of software running inside Amazon's cloud. And instead of temperature, it's observing the number of running web servers for a big online store. You, the developer, have declared the desired state. I want 10 web servers running at all times. The control loop begins. It observes the system and counts the servers. It sees 10. The current state matches the desired state. It does nothing. The loop repeats. Observe 10 servers. Compare 10 servers. All is well. Then a physical server rack loses power. One of your web servers instantly vanishes. On the next cycle, the control loop observes the system. It counts 9 servers. It compares this to the desired state of 10. There is a mismatch. So it acts. It sends a command to the cloud infrastructure. Start 1 new web server. A few moments later, the new server is online. The loop runs again. It observes 10 servers. It compares to the desired state of 10. The system is stable again. It has healed itself automatically without any human intervention. This is the secret. This simple 3-step loop, observe, compare, act, is the engine of the cloud. It is the fundamental building block for almost every major service at Amazon Web Services, Google Cloud, and Microsoft Azure. When Netflix famously created their Chaos Monkey tool, which deliberately and randomly shuts down their own servers during business hours, they weren't testing the servers. They were testing their control loops. They were proving that no matter what chaos was thrown at the system, their automated reconciliation loops would always bring the system back to the desired healthy state. They built an anti-fragile system, one that gets stronger from chaos, all based on this one core idea. This shift from giving a computer step-by-step instructions to simply declaring a final goal is a revolution in how we command machines. It's the difference between being a micromanager and being a leader. A micromanager says, first, copy this file. Second, check if server X is busy. Third, if it's not busy, start this program. A leader says, our goal is to have this program running on a server with low latency for all our West Coast customers. Make it so. The control loop is the tireless, infinitely literal lieutenant that carries out that vision. And these loops are everywhere. A database service that automatically adds more storage when it's 90% full? That's a control loop observing disk space. A system that automatically diverts traffic away from a data center that's experiencing an earthquake? That's a control loop observing network latency and health, and acting to change network routes. The entire Kubernetes project, which now powers a huge portion of the internet, is essentially one giant sophisticated collection of control loops. You declare that you want your application to have 3 copies, a database, and a public web address. Kubernetes controllers, the control loops, then work ceaselessly to forge that reality out of the raw infrastructure. This is why modern systems are so resilient. It's not because the individual parts are perfect. They aren't. Servers fail, networks lag, and software has bugs. They are resilient because they are designed with the assumption of failure. The system is in a constant state of self-correction. It's like a body's immune system, constantly patrolling, identifying threats, and neutralizing them to maintain a state of health or homeostasis. The control loop is the immune system for the cloud. What began as a way for a few hyperscale companies to manage their mind-boggling complexity has now become the standard way to build reliable software. This one pattern, this secret, unlocked the ability for a small team of developers to command an army of tens of thousands of machines as easily as they once commanded a single one. It allowed them to stop worrying about the how and focus entirely on the what. They could now just dream up a desired state, declare it in a file, and hand it to a global computer that would not rest until that dream was made real. So the next time you stream a movie on Netflix, and it starts instantly without buffering, you're not just seeing the result of fast internet. You are witnessing the silent, invisible work of thousands of control loops. Loops that are balancing network traffic, loops that are monitoring server health, loops that are replacing failed machines, and loops that are even predicting when you might want to watch the next episode and moving the data closer to you before you even hit play. You're seeing a system that has been declared into existence. A complex, sprawling global machine that is held in a state of perfect dynamic equilibrium not by brilliant engineers watching every screen, but by a simple, humble, and relentless idea. The idea that you can create order out of chaos, not by controlling every tiny detail, but by simply knowing what you want, declaring it to be true, and letting a tireless digital guardian do the rest. The secret isn't a piece of technology, it's a philosophy, and that philosophy of observe, compare, and act is the silent beating heart of our modern digital world.